welcome to ML Done. This is Mehran. So far we've covered a few applications of machine learning, and the last session we talked about learning association and classification. And we said that in classification, given an input, we'd like to classify that input into certain classes. And one of the examples that we studied was the case where a bank decides to give out loans to certain applicants, and the bank would like to know if a certain customer is a high risk or a low risk customer, so that he could decide that whether they're gonna give them give the customer, that particular customer, the loan or not. And then we talked about learning association, and we talked about basically learning the probability of a certain event given another event, meaning learning the conditional probability between two events. And we talked about the example of basket analysis, where we were interested in learning the probability of a customer buying certain product A given that they've already bought product B. And that's it. And we promised to go over the next application of machine learning, which is the regression problem. And that's what we're going to do today. Now, let's start the problem of regression by giving you an example. Imagine that we're interested in predicting the price of a car, right? So it's all about prediction here, and the scenario is predicting the price of a particular car. And my question is, what are the inputs and what are the outputs of this particular problem? So the inputs are the attributes of the car. You can think about the engine capacity, the year that the car was produced, its brand, and all other information that you could think of. And the output is the actual price of the car. Okay? Now, any such problem where the output is an actual number, and usually it could be any number. You can think of like 12.5, 12.39, 1000, whatever number you can think of. Whenever the output is an actual number, we're dealing with a regression problem whenever we want to predict that number, basically. Now, in our example, Y is the price of the car, which is the output. X is the car attributes or the inputs to the problem. And we are insisting that there is a relationship between the car price and these attributes, meaning that there's a relationship between them, there's a pattern. There is, and basically this is the essence of machine learning, there is a function that basically connects the input to the output, or the function basically, right? And here's a question: what are we learning here, and how are we going to learn it? Now, basically, we're going to learn the pattern, or that hidden function that receives X, or the input, or the car attributes, and spits out the car price. We want to find that. We want to learn that function, that hidden function. Okay? And how are we going to do that? By surveying through loads of examples, right? So we're going to see loads and loads of car attributes and the corresponding car price to those attributes, right? So we're going to see that like we can think of example as in, let's basically simplify the example where we have one input, which is the engine capacity, or the horizontal axis in this graph here, and let's say that Y is the car price, which is our vertical axis, right? Now imagine that we have loads of examples, like we talked to several companies and we gathered this data. A data such as, say, this one, say that for a certain engine capacity, the price is like this much. Let's say the price is in dollar. For the other one, a higher capacity, the price goes higher, and it goes higher and higher and higher. Okay? Now, imagine that we have thousands of these examples. Just for simplification, for better visibility, I just put like 5 crosses here. But imagine we have loads of examples. Now, what I'd like to mention here is that these examples have a name. They're called the training data. Okay, so I'd like to basically segment this part of the graph. So these crosses are basically the training data, right? Because the machine learning algorithm will go through these examples and will try to find a model, find a pattern that would describe these crosses, these data, and that could extract the knowledge that is given an engine capacity. What would be the price of that car? Okay. Now, let's say that we basically assume that there's a linear relationship between the two. Okay, now in that case, if I ask you how many possible lines are here, like how many possible lines could you come up with in this graph, well, the answer is an infinite number of lines, right? So one could come up with this line and describe this line as the best line that could pass through all my training data and be the best fit possible, right? Someone else could come up with a line like this. Now let's think about what this line really represents. It means that the more, I mean when I start with a very low engine capacity, say right here, right? Say with a very, like, I don't know, I'm not a professional on cars, but let's say 2 liters. I've got this much of car price, say, I don't know, $1,000. I know the numbers might seem ridiculous, but it's not my point here. I want to just study the pattern by which this line is changing. Now, if I just jump into, say, I don't know, like 5 liters, the price of the car would go something like very high, say $10,000, right? So this line basically says that we have a very, very fast growth in the car price as the engine capacity increases, while this other line here describes a more moderate behavior, describes a much more gradual increase in the car price based on the engine capacity. Now, what we're trying to do is we want to find the best line. Now, what does best line mean? It means that the line that fits the best in my data. As you can see, neither of these lines can describe the pattern in our data, right? Because one is too vertical, the other one is too horizontal, whereas what we've got here is a kind of mild 45-ish degree slope of a line that would pass through all our training data and be the best fit, basically. Now, let me erase this the graph. Now, much better. Now, what if we had a line like this one? Forgive my bad drawing, but I'll try to come up with a with a line as straight as I can. So the line would be something like this, kind of, right? Now, this is much better compared to the lines that we previously saw, because this has much more similarity in the pattern that we're seeing here, right? So what are we learning? Again, the question, what are we learning? So we'll go through all these examples and we'll try to find the best line by learning the best line. What does it mean? It means that I'm going to learn 2 things. I mean, if I assume that my model is a linear model. So in that case, what I'm going to learn is number one would be the slope of the line, and number 2 would be the intercept of the line, right? And these are called the parameters of, parameters. I'm sorry, bad spelling here. Let me write it again. So these are the parameters of my model. And what is my model? It is a linear model, right? So let me tell you something. Whenever we're dealing with machine learning and we are trying to learn a model, basically we're trying to learn the parameters of that model, right? So in this case, if we're assuming that our model is a linear model, it means that it has only and only 2 parameters, the slope and the intercept. So in this formula right here that you can see, y equals yx plus y equals wx plus w0. Here, x is my input and y is the output, right? So x is the engine capacity and y is the price. And we're trying to find the best slope, which is the w over here. This guy is the slope, and w0, which is the intercept. Now, you might ask, okay, hold on a minute. So yeah, those are the parameters we have to learn, but how are we deciding whether one line is better than the other? Now, this is beyond our talk in here, beyond our course, this introduction course to machine learning. But what I would like to say, just as a side note, is that in machine learning, we come up with an error function, right? That basically tells us how much we have screwed up, right? So given a arbitrary line, using that error function, I mean, let's put it this way. Your machine learning algorithm suggests a line, right, which has a certain w and a w0, or slope and an intercept. And then, using that error function, you measure how good this line is in describing your data, right? And then, based on that error that you've received, that you've computed, you will adjust the slope and intercept. You will adjust these parameters so many times until you reach to the minimum error possible, which means that you've found the best line that fits your data the best. Now, I don't want to dig into detail of that, but yeah, let's not just jump into that, because it's just beyond an introductory course such as this one. But hopefully in the next courses that I'm going to prepare, we'll go over the supervised learning in more detail, and also the unsupervised learning in more detail, where we dig into the math behind it and we really understand what those error functions are and how we can use them to learn the parameters of the model. But I'm digressing. So let's say that this red line is the one that we've come up with, and it has a certain w and a w0. Let's call that, let's say that we have found the w star and the w0 star, right? And say that our optimal model is like y equals w star x plus w0 star, right? Now, we found this using our training data, right? Now, imagine that the training is done, and now say we sold this machine learning algorithm to a company or a customer or whoever. And then, let's say the customer come up with a car with a certain engine capacity that our model has never seen before in the training data, right? Say an engine capacity of this much on this side of the graph, right? Now, well, it's just too far away, because I don't want to just slide off my slides here. So let's put it this way. Let's say the data is over here, right? a new engine capacity that the model has never seen before. And now you want to predict the price, the car price for that particular engine capacity. And you have this model that your machine learning expert team have basically claimed that this is the best model describing the car price given the engine capacity. And then, if you want to use this model, it's quite simple. So imagine this red line, right? So basically it goes to infinity, right? Now, given this engine capacity, if you go up where it cuts through the line, and then you connect this to the horizontal line, basically, let's assume that this line goes up here, right? So it touches the axis, and here, say it's $12,000. And that would be the prediction of your machine learning model, or the learned model. And this is how the model predicts the test data, which is, in this case, is this new capacity that the machine has never seen before, right? And that is how the machine generalizes the learned model, in this case this line, to an unseen data, which we would be calling a test data. Perfect. Right, so basically, look, regression and classification, right? They're both supervised learning problems. Now, I will talk about unsupervised learning problems as opposed to supervised learning problems in our next class. But just to give you a hint, a supervised learning problem is when the training data, which is in our previous example, these little crosses here, when we have the ground truth or the actual label for our training data, that's when we have a supervised learning problem, right? Because we are being supervised by a teacher. Some people call it a supervisor, some people call it the truth. Why? Because for every one of these engine capacities in our example, we basically have the actual car price provided by the owner of the data. Or basically by owner, I mean the person who has basically computed or basically gathered the data related to the ground truth. So the ground truth in this example is the car price, as right here, right? So for every engine capacity in our training data, we have the actual price, and that is the supervised learning, because we have the actual label, or in this case the actual price, the actual the truth, basically. Okay, sometimes they call it the ground truth as well. So in unsupervised learning, that's another story. We're going to talk about it later. So regression and classification are inherently both supervised learning problems. And the whole story behind machine learning, whether it's supervised or unsupervised, is to learn a hidden pattern or a hidden mapping. A mapping between two things. We'd like to know how the input is mapped to the output, right? This is the mapping right here, and this is the question, basically, right? So if it's a regression, that output is a number, and the input could be anything, could be numbers, could be categories, could be anything, and we'd like to find that hidden pattern, that hidden function over here. Let's call it G, that can successfully map input to the output, right? So in regression, as we saw, we have this particular line, and we assume that our model is a line, and the parameters that should be learned are the slope and the intercept, right? Whereas in classification, given an input, we'd like to map that input to a class. Say if we have images, and say we have classes of cat, dog, and boat, right? Given an input, we'd like to classify that into one of these categories, and for both of these cases, what we have is we have loads and loads of examples, loads and loads of training data, where we have the input and the actual output for that input. So these green crosses on the diagram on the left. So we have the engine capacities in our training data, and we have the corresponding true car price for each one of them, right? And for classification, we have loads of images, and for each one of them, we know whether each one of them belongs to either cat, dog, or boat classes. And we'll learn that mapping. So given a new image of a cat, of a dog, or of a boat that the model has never seen before, we're hoping that the model would have learned a model, basically the mapping G well enough so that it could classify that new image into the right category, right? So as we said, in linear regression, the parameters that are to be learned are slope and intercept, right? And we can generalize this idea. Let's call these parameters theta, okay? And I'm not just talking about a linear regression problem. I'm not even talking about just a regression problem. For any given problem of machine learning, let's assume that we have a certain parameters that the model is striving to learn, right? So let's say that theta over here is our parameters. And remember, parameters are the ones that are to be learned, right? Pay attention to this one, please. And the whole story behind machine learning is that we will define a model up to a set of parameters, and then we will try to learn those parameters to find that the best model, right? So in this case, if X is our input, right? So let's say we've got loads of images, right? So X's are the images, right? And say that theta is our parameters. So if it's a classification problem, we're dealing with the parameters of our model. I'm not going to jump into details about this one, but say if we're dealing with a polynomial a function that we believe would map X to the Y, and then basically the coefficients of our terms in our polynomial function would be our parameters. I'm going to dig more into detail of this one, but just another example for those of you who are a little bit more familiar with machine learning. So if you have a neural network, right? A neural network has millions of, could have millions of weights between the neurons, right? Oh, those weights are the parameters of the model, and we can basically label all of them as theta, which is the parameters to be learned, right? So when we have X given our parameters theta, so this vertical line here is basically what would be read as given, right? It's some sort of a condition. So it means that if I have my input given the parameters of our model, I would put this input into my G, that function, right? And then the result would be my Y, which is the output, right? So the point is here that we believe that, please pay attention, this is really important, that this G is not random. It means that we believe that there is no randomness here. It's not like for a given X we could have any type of Y. It's not like for a given engine capacity we could have crazy astronomical car prices or very, very low car prices at the same time. So there is a pattern, there is a rule there, right? So we believe that G is that rule, and that rule has some parameters, right? So we'd like to find the best G, right? So the goal is to find basically, let's say, the best estimate of G. So G is the truth. G is the function, the true function that we're trying to estimate. And how do we estimate that? We estimate it by learning Learning what? The parameters of the model. Okay, in the next slide I'm going to explain more what I really mean by parameters. Now, the previous regression problem that we talked about was a linear regression problem, right? So what it means in a nutshell is that we have basically the power of our input x is 1, right? Plus w0. It means there's a linear relationship between y and x. Now, not always could we use a linear model, okay? Because sometimes the relationship between x and y is much more complicated than what a line could describe, right? And basically, in this example, for instance, as you can see, there's a kind of a curve happening in here, right? And it doesn't matter how many lines you would try, a line could never describe a curve, right? So you'd like to be able to kind of bend the model a little bit and make a more say flexible model that is not as simple as a simple line, right? And that is when you resort to quadratic models where you've got W2, W1, and W0 here, and you have a square root of, the power 2 of your input as well. So you have W2x squared plus W1x plus W0, right? Or you could get even more complicated and go for polynomials of higher orders, 3, 4, or as high as you can. And this right here is the general formula for your model, right? It can get as complicated as this one. And this is a polynomial of degree n. Great, so for instance, in this case, you would like to find a curve such as this one, right? So it's something that would go along this line. Right. And if you were to use a simple linear model such as this one, you would end up with lines like, I think, well, the best line that you could have gotten would be probably something like this. But as you can see, it overestimates the price of the car in this region, right? And it underestimates the car price in this region. Because if we assume that this curve is describing the car price perfectly, so it would go high and high up to probably this region right here, and then you'll see that this green line would, if we continue that, we'd see that it falls way under the actual pattern of the data. So it's basically underestimating the car price given engine capacity of that particular region, and that is when you would resort to models of higher of more complexity, such as quadratic models, higher order polynomial models. And in this case, the parameters, so say in this case, the parameters of my model are W2, W1, and W0. So you want to find the best curve. You don't want to see a curve like this or a curve like this. No, you don't want to go there. You want to find a nice, clean, neat curve that would pass through your data the best way possible. And to those of you who are a little bit more interested, well, not interested, but more like you're not total strangers to these terms, I'd like to say that we're not really looking for like absolutely minimizing the error. I mean, by error, I'm talking about that final function that would tell you how much you've screwed up for a given model, right? So you don't want to find the absolute best fit that would pass through your training data exactly the best way possible, because that's a case of overfitting. And you don't want to have a line here either, right? So a line is too simple to describe the pattern in this in your training data. Hence, by training data, I mean the green crosses here, because that would be underfitting. You'd like a model that doesn't have too big of an error or too low of an error. You'd like just a good fit, so not underfitting, not overfitting, but you'd like a good fit. But and to those of you who are not familiar with these terms, and I think in the next module probably I'll go over these terms in more detail with good examples. But right now it would be a kind of a digression. One more thing before I wrap it up by talking about the applications of regression is that in this slide I forgot to mention a couple of important points. Number one is that, as I said, G is the model and the theta are the parameters of the model, right? And Y is a number if you're talking about a regression problem, or it could be a class label, right? So in the case of our images, the classes could be cat, dog, boat, car, or whatever you want. So it could be a class label, basically. Now, if you're talking about a regression problem or a classification problem, then what we call G would be different. So this is just a matter of terminology problem, okay? So we call G as a discriminant function, okay, if we're talking about the classification problem, because that G, what it does is that it separates the instances, the inputs that belong to class X from the inputs that belong to class Y, right? So since it separates them, we call G as basically the discriminant function, right? So let me just write it here. So in terms of classification, G is the discriminant function. And in terms of regression, so if we're talking about, let me just erase a little bit of here to have some more room. So in terms of regression, G is called the regression function. Okay, so don't be a stranger to these terms. A regression function is self-explanatory, but whenever you heard something like a discriminant function, it means that this function basically separates certain instances from some other instances, depending on the class that they belong to, right? So basically, in our images example, it's a function that can differentiate between images that belong to class cat and the images that belong to some other class like dog or boat. Right. So as I said, in machine learning, what we're trying to do, so the whole story behind machine learning or ML is to optimize the parameters or the theta that and when we optimize, that means that we basically come up with the best approximation of the truth, right? So the machine learning program tries to optimize the parameters theta such that the approximation error has been minimized, right? So it means that what we've estimated is as close as possible to the ground truth values that were given in our training data. In the regression problem, the ground truth is the actual numbers, or say in our example is the car price, and in classification problem, the ground truth are the class labels. Okay, so the whole idea is to find the best set of theta that can approximate basically the mapping, the true mapping between the input and the output. regardless of the application, whether it's regression or classification. So, as for the applications of regression, remember in regression we're trying to predict a number, okay, not a label. So think of the navigation of a robot, so for instance we've got Mars rover, right? So the inputs are, say, the angles of the metal joints in this particular robot, right? And then it could be also the images sent from a camera basically in the head of the robot, right? So the frames of images are just pouring in, and you've got sensors that are basically, say, measuring the vicinity of any obstacle nearby, or the angles of the joints of the robot. So these are the input, and the output could be the right angle by which, or basically the right direction that the robot has to go through, or the speed that the robot has to take on now based on the obstacles around it. So the speed, the direction, the angle, they are the numbers that using regression you can predict. And basically the best sort of training set that they've come up with for training the robot to navigate the unknown environment, so the best training data has been could be basically collected by basically monitoring and basically recording what a human would actually do, how a human would actually drive the robot. Basically drive the robot, or so basically given certain inputs, how would the human drive the robot in this unknown environment? And seeing loads and loads of those training data, the machine learning algorithm would finally learn how to drive this rover in an unknown environment that it's never seen before. Actually, many years ago, I remember that I saw this piece of news on TV where they had built this robot that, and they wanted to basically let it loose in the mysterious pyramids of Egypt. And what I was thinking about at the time was that, okay, so they have no idea what are the paths inside the walls of the pyramids are like. And like if there are turns there, if there are obstacles, what type of obstacles, what are the slope of the roads. But by road I mean the pathway inside the walls. So I was always thinking, like, how the hell did they come up with that robot, and how that was kind of ridiculous for them to even think that was going to work. And it did work. And guess what? That's a case of navigation of a robot problem. Right? So they might have as well used machine learning for that. I have no idea what they've done. It could have been driven by a human that could remotely access the robot through some, I don't know, wireless link or whatever. But having said all that, this could be a good example of machine learning, where in an unknown environment you try to use the learned model of your training data that you've seen before, and you'd like to basically put your robot in that unknown environment, i.e. the walls of the mysterious pyramids of Egypt, and you'd like the robot to be able to deal with the unknown obstacles as well as a human do, or close, basically. Some other example is the predictive analytics, right? So it's very interesting if you could predict the power consumption during different times of the day or seasons, right? So the power suppliers would love to know, would love to be able to predict the power consumption, say in the next 2 hours or 3 hours in a hot summer day, so that they could know that, okay, how much power do they need to supply, so they could be very well ready for any drastic requests of power from the clients, if should the need be, right? So they can basically, I don't know, like produce more power in their storages, in their batteries, or whatever they call it, so that when the time comes, they wouldn't get surprised or shocked, or they wouldn't have to cut out the power from a certain part of the city just because they were not ready for certain exigencies. Or if you could come up with a prediction model that could predict the oil price and in the next few months, or even the price of digital currencies such as Bitcoin or Ethereum, you could become a billionaire. I'm really not kidding. You could indeed become a billionaire. And that means that it's not simple. So when you think about oil price, right? The number of inputs that you have to consider before you can make a prediction could be ridiculously high. The inflation in the market, the politics, I don't know, the circulation of money in the country, the sanctions imposed on your country, or whatever it is, the demand for certain products, for oil, or for certain digital currencies. So basically you need to consider loads and loads of things, or the inputs, right? So before you can make a prediction. So in this case, the X, or your input, could be ridiculously, and I'm writing this word because that's true, ridiculously large, right? So because basically you can't consider everything, you know, there are loads of variables out there, but there are ways to do this, and well, I don't want to dig into details of that, but that's something that people are working on. So is the case of digital currencies. Now, next one could be, and the next one is the operation efficiency, right? So let's say in a call center, if you want to measure how efficient the operation of your staff is, you can basically analyze the relationship between the waiting times of the callers and the number of complaints, right? So so depending on the model that you can fit into your data, you can figure out whether whether there is a relationship or not. So if the waiting time is high, I don't know but for some weird reason you might find out that, okay, the number of complaints did not go high at all because the final service that the callers got was so good, and maybe their problems were solved by basically the person on the other side of the line, or your staff. Maybe they helped the callers so well that they didn't mind having to wait for a long time. Anyways, my point is that by using the training data, you can basically measure the efficiency of your whole organization, and that is when there's this funny motto here that I wanted to put it over here because I liked it. So it says, no more guessing, let's go data driven. It means that there is a pattern in the data, and I will discover it using machine learning. So the pattern here is that, is there a relationship between the waiting time and the number of complaints? The pattern could be no, there's no relationship. Okay. Maybe if you add more elements to your input, you would find the relationship, you would find to what the number of complaints has a relationship with. Okay, now the last category would be error correction, right? So let's you have a hypothesis, right? And you want to execute it, but before the actual execution, you'd like to test your hypothesis, whether what you thought was true or not, right? So, for instance, imagine that you have a hypothesis like, does extending shopping hours greatly increase sales, right? So you might ask your staff members to work even on the weekends, right? Just because you think that, okay, more shopping hours would increase your sales because customers could come to your store even on the weekends, right? So you might have this hypothesis, but before jumping into any conclusion and actually hiring more staff members and keeping the shop open 24/7, you might want to test your hypothesis. So this means that you might figure out that, okay, if I do that, maybe because the staff would work harder and harder for longer hours, so they would be kind of low on their energy, and they would be less interested or less motivated to serve the community or serve the customers. So eventually well, in the whole, if you look at the whole picture, you realize that the customers would receive a much more poor service compared to the case where you were closed, say on the weekends, right? So you can figure out the truth before actually executing your hypothesis. Okay, great. So coming up next, we will talk about unsupervised learning as opposed to supervised learning. And we'll talk about the examples of unsupervised learning, one of which is clustering. And you can use this in many different applications. And in supervised learning, we'll tell you that, okay, as opposed to supervised learning, you don't have any, and I mean any, access to the ground truth. All you have in your training data is the X, right? So the training data, let me write it over here. So the training data has, and I couldn't stress this enough, no ground truth. Crazy, huh? So basically, you don't know what the truth is, and you'd like to figure out the pattern, the mapping pattern that can describe your data to whatever the truth is, right? So you don't have the truth anymore. You don't have the mapping anymore. You don't have that relationship in your training data anymore. So all you have is the data, and you'd like to understand your data the best way possible, and that is when clustering comes in, where you try to cluster similar data together and see if there's a rule there, if there's a pattern there. We're going to talk about this more. Clustering is one of the most interesting areas of machine learning, and logically and expectedly, unsupervised learning is, well, at least in my opinion, I would say, more useful than supervised learning, because unsupervised learning is when you don't have, say, in a classification problem, you don't have the labels, right? Because having labeled is labor, right? Labeling your data is hard work. It really is. People hire staff to label their data. People do that as social experiments, as like they would ask for volunteers who would just do a couple of clicks in a day to just label the data. So they would show them pictures, and they would ask them to map the pictures to the correct class. Like if you see a cat, you would just click like check cat in some sort of a multiple choice question, and at the end they might offer you coffee or a free t-shirt or something. So labeling data could be expensive, and it could be time consuming. So because of that, there are loads of data out there that have no ground truth associated with them, right? So that is when unsupervised learning comes along, and that is why I'm saying that's due to the prevalence of unlabeled data. Unsupervised learning seems to be the way to go. We have another class called semi-supervised learning, where we have the ground truth for a part of our training data, and we don't have any labels or any ground truth for some other part of the data, and that is called semi-supervised, because it's neither fully supervised nor fully unsupervised. It's somewhere in between. And then we'll talk about the applications of unsupervised learning, such as the image compression, or the things, well, I don't want to talk about it now. We're going to talk about it later. Yeah. Well, look. I don't believe it. We've already finished regression, and I really hope that this has been informative for you. That was quite exciting for me as well. So just to wrap it up, well, we said that regression is different from classification, in that we're trying to predict an actual number, whereas in classification we're trying to predict a label, which is the class label. Okay, and we said that the model G that we're trying to estimate, if it's a regression problem, that's a regression, say, function, And if it's a classification problem, it's a discriminant function. In terms of terminology, we clarified that, and we talked about the some of the applications of regression. I hope that this has been informative for you, and on behalf of ML Don, take care of yourselves.